Let's start with Albert Einstein. His Nobel Prize-winning work on the photoelectric effect shifted how physicists measure and track light and energy. The core mechanism is quite straightforward. A single packet of light, called a photon, strikes a metal surface and knocks loose a single electron. You can think of this as a strict financial transaction. You have your incoming energy minus a toll collected by the metal, leaving you with the electron's leftover speed. We can translate that exact receipt directly into Einstein's photoelectric equation. This formula shows the relationship using the frequency of light. Let's look at the terms. Here, h nu represents the incoming quantum of energy from the photon. Phi sub 0 is the work function, which is the specific minimum energy toll demanded by that metal. Subtract the toll from the incoming energy, and you get K max, the maximum kinetic energy of the escaping electron. Because the frequency of light is directly related to its wavelength, we can easily rewrite this equation. By swapping out frequency for the speed of light divided by wavelength, we get a second, equally useful version of the formula. Whether a physics problem looks simple or complex, it ultimately boils down to this single rule of energy conservation. Now, let's look at a critical edge case. What happens if the incoming photon brings exactly enough energy to pay the metal's toll, leaving the ejected electron with exactly 0 leftover kinetic energy? If we take our main equation and set the kinetic energy to precisely 0, we can solve for the absolute minimum frequency required to break an electron free. This specific value is called the threshold frequency. As the resulting formula shows, it is directly proportional to the metal's work function. We can analyze this exact same boundary state from the perspective of wavelength instead of frequency. There is a crucial mathematical difference here. Because wavelength sits in the denominator of the energy equation, finding a minimum energy requirement actually dictates a strict maximum limit for the wavelength. We define this maximum limit as the threshold wavelength. If the incoming light's wavelength is longer than this value, the photon won't have enough energy to pay the toll. You can think of every specific metal as an exclusive club with a strict gateway. To trigger the photoelectric effect, the incoming light must possess a frequency above the threshold frequency and a wavelength below the threshold wavelength. Let's map this physics equation onto a coordinate plane. Einstein's formula perfectly mirrors the standard algebraic equation for a straight line. K max maps directly to y, frequency maps to x, Planck's constant maps to the slope, and the negative work function maps to the y-intercept. This is a graph plotting the maximum kinetic energy on the y-axis against the incident frequency on the x-axis. Looking closely at the intercepts, the exact point where the solid yellow line crosses the x-axis represents the threshold frequency. If we extrapolate the line backwards down the y-axis, the intercept gives us the negative value of the metal's work function. The slope of this line represents Planck's constant. Because Planck's constant never changes, if you graphed the threshold frequencies of completely different metals, they would all produce perfectly parallel lines. Graphing the data like this gives us an immediate visual fingerprint of any metal's unique energy toll. If wavelength lambda produces kinetic energy E, what new wavelength doubles it? First, substitute E into the equation. Next, write the doubled state. The identical work function remains. Subtract the first equation from the second to cancel it, then rearrange to solve. Before we finish, pause the video for a moment and see if you can write out the basic maximum kinetic energy equation using only the wavelength variables, completely removing the work function term. By treating the photoelectric effect strictly as an energy transaction and keeping track of the inverse relationship with wavelength, you can systematically dismantle any complex problem thrown your way.